So here's our situation for problem number 50. We have this cube nailed to the wall, and at the corner of the cube is a spring attached, and we're going to displace it by this angle, theta max, which will in turn stretch that spring, and then we'll release it, and it will oscillate back and forth like this. They give us a couple of pieces of information. They tell us the mass of the cube is 3 kilograms. The K constant of the spring is 1200 newtons per meter. The dimensions of the cube are given, and the maximum displacement before we set it into oscillation is 3 degrees. The problem is asking for the period of the resulting oscillation. So how do I go about starting this? Well, if I realize that I know this cube is going to have maximum angular speed at the equilibrium position and 0 angular speed at the maximum displacement. So if I can use my equation for angular velocity, maybe I can solve the problem using that equation. And I also know that out here at the maximum displacement, that's when all the energy of the system is stored in the spring. And then when it's here at the equilibrium position, the spring will have no energy stored in it, and now all of that energy is in the form of rotational kinetic energy of the cube. So let's use our conservation of energy methods then. So that's what I'm saying here, that the potential energy stored in the spring when the displacement is 3 degrees is the same as the rotational kinetic energy of the cube when the angular displacement is 0 degrees. Now the energy in a spring is 1/2 kx squared, and that x value, that's going to be this short distance right in here that the spring gets stretched. So that's what this x max is. And then we know kinetic energy of a rotating object is 1/2 I omega squared, where this omega is the angular speed of the rotating cube. So I'm going to solve this equation for omega squared, and I'm calling it omega max, because keep in mind, that's at this location, that's where the angular speed is the greatest. So I'm calling it omega max. So when I solve that equation, here's what I get for omega max. Now that is the maximum angular speed. My equation for angular speed at any time is right here. Omega t equals negative theta max times omega sine omega t plus phi. And that's, of course, what I got when I took the derivative of my equation for displacement, which is angular displacement at any time t is equal to my maximum angular displacement times the cosine of omega t plus phi. That's my general form of the equation for simple harmonic motion. So when I took the derivative of this with respect to time, this is what I got. Okay, now at the maximum speed, I know that's when this part of the equation is 1. Okay, so I can just set that equal to 1, and now my equation simplifies to my maximum angular velocity or maximum angular speed is equal to my maximum angular displacement times the angular frequency. So be careful. We've got the omega variable in the equation twice, but it stands for 2 different things. Over here, this is the angular speed of the rotating cube, and over here, this omega is the angular frequency of the simple harmonic motion that the cube is undergoing. And for angular frequency, I know that is equal to 2 pi over t, and that t, that is the period of the oscillation. This is what the problem is asking me to find. So that's what I'm looking for right there. All right, up here I found that the maximum angular speed is equal to that, so I will make that substitution right here, and then I will make this substitution right there, and now I'm going to try and solve this equation for t right there. K is the K constant of the spring. I know that. I is the moment of inertia of the cube. It wasn't given to me, but it did give me the dimensions of the cube and the mass of the cube. So I'm going to be able to figure that out. Now, how do I figure out what is that displacement? Remember, That's that small distance right there that the spring is stretching. So how do I find that? Well, when I look here, I see that when the cube rotates, this is a zoomed in view of the cube, these 2 points are when the top of the cube is here and there. So there's 2 ways you can look at it. You can say, yes, that is an arc length, but it's such a small angle that that arc length is really just about the same as the straight line distance. So that's what I'm saying there, that S arc length is approximately equal to X, the stretch of the spring. You can think of it that way, or you can also look at this as a triangle, and this is the opposite side. So X is equal to R sine theta, but the small angle approximation tells us that for very small angles, theta and sine theta are about the same. So either way, I come up with X is equal to R theta, and that theta is the maximum displacement of the cube. So that's what I've done here. I've replaced X with R theta, and then I replaced this omega, remember, with this expression here. There it is. And now I can solve this equation for the period. The theta maxes cancel out, and I get 2 pi over r times the square root of I over k. So here's my calculation for the moment of inertia of the cube. This is the equation from table 10-2. The mass of the cube is 3 kilograms. Each side is 6 centimeters. So there's my value for moment of inertia. And the last thing I have to find is this r value. So here's r in my diagram. In the cube, that's where r shows up. So using Pythagorean theorem of this right triangle right there, I can solve for r, 4.24 centimeters. There we go. I plug it in, and ta-da! Period of oscillation is 0.18 seconds.